Hello, everybody. Okay, perfect. Yeah, so first of all, big thanks to the organizers for having me here. It's a really nice conference. So I hope you're not tired yet of cosmology and astrophysics. So we just had a nice break with something very different. So okay, so this talk, the first half is going to be about simulation-based inference. So I hope everybody's can take something away from it. And then the second half of this talk will focus on cosmology and astrophysics specific applications of simulation-based inference. And so one of okay. Anyway, I can do this. So when I first heard about this workshop here in Vipava, so this the name somehow kind of rang a bell, but I didn't know where. And then I remembered that there's this famous ultra trail Vipava Valley. I don't know if some of you know this. Yeah. So basically, so it's every spring, and you can run up to 165 kilometers. You get 46 hours to do it. And you can still sign up. So if you're interested in doing this, so it goes here through the mountains behind us. So if you're interested in this, then you can still sign up for it. Okay, but let's start with the science. Okay, so what do cosmologists do in astrophysics? I mean, so there are all these beautiful galaxy images that we get from telescopes. So this is, for example, from the James Webb Telescope. But of course, I mean, this is beautiful, but we want to use this data to do actual science with it, right? And I mean, so we've already heard quite a bit about these things. I mean, we want to answer questions like, what is the universe made of? I mean, we know that there's probably dark matter, there's dark energy, but what is it? How fast is the universe expanding? And all these kinds of science questions. But so if you look at this problem kind of from a more abstract perspective, then it's basically just this. You have some data and you want to infer some parameters, right? So this is kind of the entire framework that probably applies to many other scientific disciplines as well, right? And so in astrophysics and cosmology, people often use Bayesian statistics. So we have already heard quite a bit about this now. So in principle, what you want to do is you want to derive the posterior probability for your parameters theta, given some the data that you've observed here. And so then Bayes' theorem tells you basically you can compute this from your prior belief in your parameters theta times the likelihood, which basically tells you the probability to observe some data given the parameters, divided by the evidence, which is basically the marginal likelihood, right? So I know people here come from very different backgrounds. So I think probably most of you are familiar with Bayesian statistics, right? So it's has anybody never heard about Bayesian statistics or never worked with it? Okay, anyway, let's start with a quick warm up, so that we're just all on the same page, right? Okay, so assume in this case we have a one-dimensional parameter space and a one-dimensional data space, right? So we have data versus parameters, and assume we know the joint distribution of both, right? Which in practice will never happen, but just assume it for now, right? Okay, so let's look at this banana-shaped joint distribution. And so if I ask you, what should be the prior distribution in this case? Just think about it for a second, what it would look like. So kind of the prior, in case you haven't measured any data yet, right? Okay, so the answer is, of course, you basically just need to marginalize this joint distribution over all the data, which you haven't observed yet. And then this gives you this, this prior. Okay, makes sense? All right, okay. Now let's look at it at a different problem. So assume you have some parameters, theta naught, and now you ask yourself, what is the likelihood to observe some data given this parameter? Okay, think about it again, please, for a second. What would this look like? All right, okay, so this would basically just be the cut of this joint distribution and where the parameter is fixed, and then so you get this bimodal likelihood, right? The probability to observe data given this parameter. Okay, let's finally do it the other way around. So now, given that you have observed some data, D naught, what would the posterior for your parameters look like? Okay, and the answer is probably as you have expected, of course. So now it's a cut of this joint distribution, but kind of in the other dimension, right? So this is now this kind of this unimodal cut through this joint distribution. Okay, so I hope now it's clear what the difference between likelihood, posterior, and so on is, and kind of so Bayes' theorem basically is a really nice way of combining all these different ways of looking at at data and parameters, and inferring one from the other. Okay, so after this short excursion, let's go back to our example. So okay, let's say for this beautiful image of galaxies, I mean, we want to infer the posterior, but to do this in the Bayesian framework, we need to think of the likelihood, right? So what does this mean? This means that we need to understand basically how the parameters affect the data that we're observing, right? But I mean, just consider this example. I mean, so we know that galaxy formation is like on small scales, it becomes highly nonlinear, non-trivial. You have feedback mechanisms, you have stars exploding, going supernova, you have black hole feedback, and so on, right? So it's kind of a really complex process on many scales that is coupled, that is stochastic, and so on. So like, I mean, on large scales, you can make some approximations. So in Urstock, we have already heard a bit about this, but in principle, it's like there's no way of writing down the correct physical likelihood for such a case, right? Okay, but so what we can do is we can sample from the joint data parameter distribution, right? So how do we do this? I mean, okay, people have been running cosmological simulations, for example, for decades. So, okay, what do you do there? Like you specify your parameter space theta. So you specify all cosmological parameters, you specify the astrophysical parameters for the feedback and so on. Then plug everything into a big simulation tool and then simulate how the galaxies evolve, basically. And so this movie is taken from the Eagle simulation. So what you see, so this TH in the lower left corner, this is the age of the universe. So now the universe is 2 billion years old. And so like the lower left half shows you the dark matter distribution. And the upper right half shows you the gas temperature, right? So you can see now, so dark matter is collisionless and pressureless. So it just starts clustering together and forms these dark matter halos. And then you can see how the gas in the upper right half basically falls into these gravitational potential wells that the dark matter has created. And then you see also, like in the gas panel, you see all kinds of heating processes. You see like the gas is basically moving around. And yeah, so this is then how the galaxies form, right? And okay, so now we're already 13 billion years after the Big Bang, and so now 13.8 years after, sorry, 13.8 billion years after the Big Bang. This is now the present time, right? So this is kind of the simulation of how the universe would look like now. Okay. But okay, so the takeaway from this is really, so we can plug in these parameters into our simulation, and we can get a sample of what observations would look like for these parameters, right? And so this is basically what simulation-based inference is about. So it's really the art of doing inference when all that you have are samples drawn from the joint distribution, like in the absence of an analytic form of the likelihood, right? And so this is why simulation-based inference is also known as likelihood-free inference, because you don't have likelihood, or it's also known as implicit inference, right? Okay, so in the rest of this talk, I will be talking about first about the traditional way how people have done SBI in the past, like mostly using approximate Bayesian computation, then using like neural networks, using deep learning basically, which is the modern approach. There are three different flavors that we will be discussing. So neural posterior estimation, neural likelihood estimation, and ratio estimation. And then I will show you some applications in cosmology and astrophysics. Okay, so this is what people have done in the past. So this is known as approximate Bayesian computation. And there, so okay, assume you don't have a likelihood, right? So how can you still get a posterior distribution? And so one idea is, which is probably kind of obvious if you think about it. So you can ask yourself, which parameters, like if you plug them into your simulator that you also need, which parameters then give you an observation that looks similar to the observation that you actually made in the sky, right? Then probably it's a good parameter. This is kind of the idea. So what you do in practice, you have this prior probability for your parameters. You just sample from this prior. For example, here it's just a, where's the mass? Okay, so it's just like a normal distribution. So you just sample, different values, 0.4, 0.2, 0.3, and so on. Then you plug this into your simulator. You get out some observation, which in this case is a histogram, but could be anything else, right? Then you compare this observation to your actual data, which in this case is this thing. And if your like simulated observation for parameter matches well your observation, then it was probably a good parameter to start with, right? And then you accept this parameter. So kind of what you need is some metrics, and I wrote it as a norm, but you need some metric to compare your generated observations to the true observations. And then if they're close enough, then you accept it. So, okay, so this method works actually quite well in practice, but there's some downsides to it. So like, first of all, of course, it like your posterior approximation then depends on this threshold epsilon, kind of that you need to choose in order to determine if you're close enough to your observation or not. So if you choose this epsilon very large and accept everything, then you will get very wide posteriors, right? If you choose the epsilon too small, then like the chance that you draw a sample from the prior that leads to an observation that is so close is very small. So you need a huge amount of samples, right? So you need to find some trade-off. Also, like this thing has, so we've already heard before about the curse of dimensionality. And so this also applies here very much. So kind of, if you have a very high dimensional parameter space, then the chance to draw a parameter that leads to an observation that in all features, in all dimensions, is close to your observation is tiny. So then you will sample kind of forever and not find anything. So what people usually do is they then compress the observations to summary statistics, but then of course you lose information again. And yeah, so okay, so is there nothing better we can do? And like, so with, you know, the machine learning revolution and so on, it turns out, yes, we can do better. And so, so as you all know, I mean, I don't need to focus on this, but so neural networks are universal function approximators, so they're especially good at modeling very complex high-dimensional functions. And so if you think about how neural networks learn, actually, I mean, neural networks are trained on samples, on individual data points, right? And so this is exactly the setting in which we're in for simulation-based inference, because we don't have an analytic likelihood, but we can draw samples from the joint parameter data distribution, right? Which is kind of analogous to how a neural network is trained. So, so kind of the modern approach to SBI is that you train a neural network basically to estimate a probability density function. Okay, so we have already heard before a bit about normalizing flows. So yeah, so Uros talked about it, so I don't really need to go into the details, but so kind of the basic idea is, so of course, if you want to model a probability distribution function with a neural network, you need to make sure that it is an actual PDF, so that it's properly normalized. So how do you make sure that this is the case? So you kind of define a neural network. So you start with a known distribution, like just a simple standard normal distribution, then parameterize like a series of invertible differential transformation. So with a neural network, and then you can go back and forth from data distribution to the known distribution and sample and infer likelihoods. I will not go into too much more detail because so Urs already explained this. Okay, so then kind of once you have a neural network to estimate probability distributions, then you can ask yourself, what exactly do you want to describe with a neural network? So like probably the most straightforward thing that you can do is you can directly train a neural network to infer the posterior distribution, right? Because I mean, this is the quantity that you're interested in. You want to get a distribution for your parameters, right? And so if you look at the loss function, I mean, you just kind of minimize the expected log posterior. Yeah, and so like one advantage if you do it like this is then kind of you can just evaluate your neural networks on many observations. You don't need to run any MC sample or whatever, because you already get out the thing you're interested in, which is the posterior, right? So kind of if you want, like if you have many data points for which you want to evaluate your neural network in the end, then probably neural posterior estimation is a good choice, right? Because it's very fast in this sense. A disadvantage is that basically by inferring the posterior, you have already built the prior into the inference. So like if you want to change the prior later, then you need to do some reweighting. It's not impossible, but it requires a bit of work, right? Okay, so an alternative is to do neural likelihood estimation. So if you look at the loss function, so here the theta and the d are swapped, right? So now you estimate the likelihood, so the probability to observe some data given the parameters. So the prior is not involved here, which means that kind of if you want to do now the sampling at the inference time, then you need to run your MC chain as you would usually do it in the explicit framework, right? With the only difference is that now the likelihood is a black box that was learned by a neural network, right? But you still have the sampling process. But Yeah, so also here I won't go too much into details because Urs like showed it. This can have some advantages to do it like this, and the neural network can potentially kind of gain a deeper understanding actually of what's going on. But it's often also more complicated because like because the observation lives in a much more high dimensional space than the parameters, right? So it's often more challenging to do. And so in Christopher's talk, we have already heard a bit about neural ratio estimation, and so like he even had exactly the same plot. So you've already seen this, but I think it doesn't matter if you see it twice. And so yeah, so what you do here is you estimate the ratio between likelihood and evidence, which is the same as the ratio between posterior and prior, which is also the same as like the ratio between the joint data parameter distribution over the marginal data parameter distribution, right? And so kind of what is the big advantage of this approach is that you're not estimating a distribution, but you're estimating the ratio between two distributions. So this means you don't need to care about using normalizing flows, whatever. You can just take whatever neural network architecture you like. It just predicts a number, right? Which is the ratio between two distributions. So this is very nice. And so as Christopher has also mentioned before, already, like the way these things are typically trained is as a classification task, right? So you basically just train a classifier. So you show to this classifier samples drawn from the joint parameter data distribution. So in this case, for example, we have images of whatever things that kind of match the label, which would be the parameters, you know, like an image of the star, image of Mars, and so on. And then like we scramble the labels, the parameters, and then this corresponds to the marginal distribution. Right, and so, okay, if you phrase this more mathematically, then you just use your standard binary cross entropy loss, kind of, and have this as a classification task, where here this is the joint distribution and this is the marginal distribution, and so you can show that this binary cross entropy is minimized by the log likelihood to evidence ratio. Okay, okay, so which of these three methods then should you use in practice, right? Okay, of course, the answer is it depends. It depends on what you want to do and so on. But so kind of as a rough rule of thumb, I mean, often it's more easy, like it's easier to go from something high dimension to something low dimension, right? So for example, if you have a huge, like say a catalog of galaxies, right? Like a huge parameter space, it's probably easier to use neural posterior estimation. Like if you want to estimate some cosmological parameters, like how much dark matter is there in the universe, how fast is the universe expanding, it's probably easier to feed this huge dimensional thing to the neural network and train it to predict something low dimensional, right? So this is kind of one rule of thumb. But of course, it also depends a lot on the shape of the likelihood and the posterior. So like if you look at this toy example here, in this case, the likelihood is bimodal. And like to achieve to model such a bimodal distribution with a normalizing flow is actually not trivial, right? Because like all the transformation in normalizing flow need to be differentiable and invertible. So kind of you start with this kind of unimodal distribution, then you want to have some mapping that splits up this peak into two. So this is not so easy to achieve. So in this case, it would probably be easier to just train the posterior, right, which has a much simpler shape. But then again, it depends kind of, do you want to do the inference for many points? Do you want to maybe consider different priors and so on, right? Okay, so this was kind of the theory part. And now we'll be considering like 5 applications to astrophysics and cosmology. So this is really kind of a completely like personal choice by myself. So there has been a lot of work on SPI and astrophysics and cosmology. So if you have done something great and I don't mention it, then don't take it personal, please. Yeah, so I will talk a bit about galaxy clustering, about gamma ray astronomy. So we've heard already quite a bit about this in Christopher's talk. About strong lensing, gravitational waves, and reconstructing cosmic initial conditions. Okay, so galaxy clustering. So this is basically like the example that I used as a motivation, right? So kind of imagine you have a catalog with many galaxies, and now you want to infer cosmological parameters from it. Okay, so okay, let me just mention. So Urs talked about something similar in the context of weak lensing. So in weak lensing, basically what you do is kind of you consider the shapes of galaxies. In galaxy clustering, you just consider the positions. But like the rough ideas are basically similar of the two. Okay, so if you look at the upper row, so this is actual data from the BOSS survey. So each point here represents a galaxy. And so now if you want to apply simulation-based inference, what you need, of course, is like a forward model, a simulator that produces like basically an entire pipeline that produces galaxies that look like the actually observed ones. So this is not an easy thing to do, but so this is now from the paper by this SimBig collaboration. And so they set up this entire pipeline. So they ran the dark matter n-body simulation, then they ran a halo finder kind of to find dark matter halos, which then they populated with galaxies, applied survey effects and so on. And what they ended up with is shown in the lower row. So these are mock galaxies produced by the forward model. And so just visually, if you look at it, I think they did a pretty great job. It looks very similar to the actually observed galaxies. Okay, and then what they did in this paper is, so here they estimated, so they recovered cosmological parameters using SBI from like using neural posterior estimation. And so, okay, so if you don't know what these parameters are, it's actually not that important, but so this is the matter content in the universe. This little h is kind of how fast the universe is expanding. Okay, and so the orange contours here, these are the constraints with their SBI when applied kind of to the entire field of galaxies, right? So kind of they use these orange contours, they use the entire information that there is. Then the gray contours, this is also SBI, but applied to a summary statistic. So first you take your galaxies, then you compress it to a power spectrum, which is what cosmologists often do. And then you do the SPI on it, right? And so this black dashed line here, this is the traditional approach where you can only consider very large scales because on the smaller scales you don't understand what's going on basically. And so you see here SPI gives you the tightest constraints, right? So it works actually quite well. Okay, next example is, so we've already heard quite a bit about the gamma ray sky. So this is the sky as the Fermi satellite sees it. And so as Christoph has already mentioned, so if like, so there are many components in the gamma ray sky that we understand well, right? So you can just basically fit them, subtract them. And if you do this, then what remains is this roughly spherical axis that has come to be known as the galactic center axis. Right? And so this emission could come from, for example, from dark matter annihilation, which would be very cool because we don't have a direct kind of signature from dark matter yet. It could also be a population of faint millisecond pulses and so on. Right, and so we've already seen what a source count distribution looks like. So this just basically tells you for distributions of point sources, how many counts come from bright sources, which would be on the right, and how many counts come from faint sources on the left. Right, and so what we did here is, so here we used like a kind of simple form of neural posterior estimation, and just kind of trained our neural network to first estimate how much flux comes from each of these emission components, right? And so then we found, so we also found that 8% basically of the flux in the data are due to this galactic, due to this galactic center axis, right? And then we trained the second neural network to also extract the source count distribution. And so what we found is basically that if this galactic center axis is made up of point sources, so of millisecond pulses, then you need a very large amount of millisecond pulses. It should all be individually very faint, right? Okay, then 3 months later, there was another paper by Sid Mishra Sharma, and they did something similar. So they used normalizing flows, also inferred the template normalizations, also inferred the source count distributions, and actually, they got very similar results. So they also found that 30% of the galactic center axis seemed to be consistent with dark matter, but the galactic center axis could also come from a large number of very faint millisecond pulses. So this is pretty consistent with what we found. And so like, as you see, like all these papers that I mentioned here, and so this is really a problem where now many people are working on using simulation-based inference, kind of trying to find out what's going on. Okay, I think given the time, I will maybe skip this. Okay, next example, gravitational waves. So inference of gravitational waves. In general, it's very tricky, right? Because like you have non-Gaussian, non-stationary noise, right? And so the thing is, in future, the analysis of gravitational wave data will get even more difficult because so kind of the sensitivity of these gravitational wave instruments is now increasing. So like we will come to a point where you will have multiple signals, like from different black hole binary mergers, we'll have multiple signals measured at the same time, right? And then you kind of need to disentangle kind of which part of the signal. So this is a typical signal that you see here. So kind of you have two black holes spiraling around, right? And you measure some strain on Earth. And so if you have multiple of these signals at the same time, you need to disentangle which one comes from which event, right? And so what they did here in this paper is they trained a truncated marginal neural ratio estimation algorithm, basically to localize gravitational wave events in the sky, which works quite well. I mean, so they found it pretty much as good as like the traditional method, but with way fewer samples. And then in the next paper, what they did is so they actually tested this on overlapping signals. So they really injected two different gravitational wave events, which you can see here with like the blue curve and the light blue curve. And they were actually able to extract, for example, here the mass of the binary black holes, almost as well as if these signals had been observed individually, which is quite impressive, right? Because I mean, the combined signal of these two things is just a mess of, you know, these things added up together, but you can still, using simulation-based inference, you can still extract the individual components, which is quite cool. Okay, last example for today is, okay, so just some fractions of a second after the Big Bang, right? You had these tiny overdensities and underdensities in the universe, right? And then basically these difference, like this really tiny difference in density, they kind of collapsed over 14 billion years of cosmic history into the structures that we're seeing today, right? And so now the question is, given this nonlinear present day density, so the kind of the density of matter that we observe today, can we reconstruct the like the density fluctuations, how they were like just fractions of a second after the Big Bang? And so this, of course, it's a quite high dimensional problem, because kind of each voxel is a parameter itself, right? And so, so this is a project led by a collaborator of mine, Oleg Savchenko in Amsterdam. And so here the idea is to use neural posterior estimation, but we're making very strong assumptions, right? So kind of we're assuming that we can model the posterior as being Gaussian with a diagonal covariance matrix in Fourier space. And like, so this assumption, in this case, it seems to work well enough. And like, due to these strong assumptions, we can sample very fast. So here, here you see different samples of these initial density fluctuations. And so at this resolution 128 cubed, we can generate 1,000 of these posterior samples in a single second. Right? So traditional methods using Hamiltonian Monte Carlo, they would sample days to get samples. And we can, like with this approach, we can get 1,000 in a single second. All right. And so if you look at the statistics, they are also actually consistent with how they should look like. Good, yes, this brings me to the conclusions. Okay, so what is SBI? So SBI really enables, so if you're in the situation that you have samples, like data samples, but you don't have access to an explicit likelihood, then SBI enables you to do data analysis. I think probably the next point is not so important for the audience here, but it's more important for a science audience. So, you know, people are still kind of afraid of using neural networks because they think it's black magic and so on. But so simulation-based inference is really deeply rooted in statistics. So you kind of, even if you're using deep learning and neural networks, you're still doing statistics, right? And so I think kind of maybe the community needs to be convinced a bit that you're kind of, yeah, that you're not doing anything fishy. So, okay, then the way of kind of moving from this traditional approximate Bayesian computation to something that really gives you excellent results. So this is really kind of enabled by neural networks, right? Because you need this expressiveness to model these high dimensional distributions. Yeah, and another thing is that if you do it with SBI, you don't need to think about this these handcrafted summary statistics that we have also seen in Uro's talk, you know, bispectrum, wavelet transform, whatever. You just take basically all the data that there is, you don't compress it, and you learn this high dimensional distribution, which is kind of a big advantage because you really exploit the full information that there is. Okay, so thanks. I will just leave you with a slide on some material that I think is useful for SBI, also some software. So thank you very much.
Thank you. Thanks. Question?
So on your next to last slide, did you have any noise here?
No, okay, this is really, it's proof of concept. And okay, I can imagine the next question that you're about to ask. So how does this work in practice, right? With the survey mask and so on? It's, yeah.
No, I wasn't going to ask about that. I was just going to make a statement that I guess likelihood-based analysis have been done of this and they get perfect results. So, and instead you get cross-correlation coefficient, I guess, going to 0 at k of 0.4.
So, okay, so this, I don't know if you know the paper by Le Chan et al. They do it with diffusion models. It's from last year, this paper. And so like our results just match their results exactly.
Yeah, but my point is that likelihood-based analysis I mean, people have done likelihood-based analysis and they get perfect agreement with, and so I guess what I'm trying to say that you're still not getting the full information is hard, right?
Yeah, but I mean, so, okay, so to just kind of quote what they say in the Le Chan paper is, I mean, okay, so on the smaller scales, right? I mean, the information is lost. Like on scales kind of that have shell crust, like there's no chance to kind of recover what happened on these scales, right?
No, I don't agree. I mean, you can look at our papers, for example, we get perfect reconstruction of K of 1 if you have no noise. So there's no shell crossing at K at 0.3 or 0.4.
I'm not sure. Okay, but we can discuss that. But so like these results match what you do in the diffusion paper, for example.
Yeah, sure.
And it's like 100 times faster. Okay, but we can discuss.
But they're both suboptimal. That's my point.
Okay, we can discuss. Yeah.
Sorry.
Hello, quite wide-ranging presentation. I have a very specific and maybe even trivial question about the ratio of the different probabilities you showed on one graph. One thing I'm not, so that's a nice idea to avoid the normalization issues. However, I don't exactly see how that number cannot end up negative or 0. How do you ensure positivity of that ratio? Because in normal classification, you have a softmax, you can just sort of force it in the right interval you want. But here, I suppose you want those probabilities to come out positive naturally.
It's actually, it's a good question. It's the same, like it's the same basic softmax. I mean, so softmax you would have for a multi-class classification, right? So here it's in this framework, it's just a binary classification, right? You have two classes, kind of joint distribution and marginal distribution. So what you have is a sigmoid function. So this sigma here is a sigmoid function.
Okay.
So it has the same effect as softmax in the multi-class classification.
All right. It just wasn't obvious from the.
Okay, it's a good question. Yeah.
Okay.
Yeah.
Okay. No, this is about galactic center excess, but I think it relates to the rest. So it's mostly these like models versus real data and reality gap question. So because when we didn't use SBI, but Bayesian networks or some similar, and then on training, on test data, we got, good results, but then we noticed we get different results given different models that we use. I mean, models of physics that we use. So SBI, I mean, it's prone to these kind of issues, right? Because you use the simulator, you depend on the simulator, right? Yeah, so just comments in that direction, like reality gap.
Yeah, this is a very good point. I mean, so this, of course, it's a big limitation of, like, I think not only of simulation-based inference, but of data analysis in general, right? I mean, what you can get out is only as good as your model of it. In that, so you write a paper about, whatever, analyzing the gamma rays kind of these 5 pages, and then you have an appendix of 30 pages where you analyze what if you vary this and what if you vary that. Because, I mean, so for example, we take these templates and they're completely fixed. I mean, but of course, this is just an approximation. So like what you should probably be doing is to also give, so there have been approaches where people give some freedom to these templates, right? Where you use, say, Gaussian processes Yeah, so this is something you should kind of, yeah, that you should do, because it's, I mean, in cosmology and astrophysics, you only have one sky, right? You need to live with it. You cannot compare it to something else. Yeah.
Another question. I have a question. If I can, it's an ill-posed philosophical question about your
I think
last.
time for lunch.
No, about your last slide. So you said, oh, that's great because then you can work directly on the field level and you don't have to go through summary statistic and figure out what are the best summary statistic. But so let's say you have the, perfect simulation, you believe it, and then you throw your real data and then you get this great inference of all of your cosmological parameter. Is that what we're after? I mean, did we learn anything about the universe then? Do you know what I mean?
Okay. Yeah. Okay. It's a good question. I mean, so kind of what do you learn? I mean, okay, these things, they're all black boxes in that sense. So so assume you get an estimate of the Hubble parameter, let's say of the Hubble constant, to 0.001%. And your question is kind of, without knowing how we got there, what do you learn from it? Right? I mean, you still know that it's a good question. I mean, I could answer diplomatically. I mean, there are many efforts kind of to make these things more.
Non-diplomatic answer.
Sorry?
Go for the non-diplomatic answer.
No, I mean, there are many attempts kind of to make these things more interpretable, explainable. Like you could take neural network outputs and people apply symbolic regression, where you can get an analytic fit to something. So there are many attempts in this. I mean, so there was a talk yesterday, also about kind of this interpretability aspect, that it's in the social sciences, for example, it's very important. And I think kind of to a certain extent, it's also the case here.
Yeah, I realize I'm also unfair. It's not like the power spectrum is really interpretable. I mean, like you know where the information is coming from, but yeah, maybe more, yeah, I don't know. Thanks.
Yeah.
Thank you.
Hmm.